Sure. Hello, everyone. Welcome to Math 1510, Deep Learning Theory and Data Science. I wanted to begin today's lecture with a small reminder. It is not the last lecture. So we were supposed to have the presentations next week, but due to popular demand, they were delayed by a week. So next week, there will be more presentations. And the week after that, we'll have the students' presentations. And I do hope everyone attends the students' presentations, because I do hope everyone gets to listen to all the other students. Because I think that's, I don't know, when I was, yeah, this is right. So I wanted to start with a small reminder of what we discussed in the previous lecture. So we discussed infinite width multi-layered perceptrons, and we discussed how there's something called the neural network Gaussian process, and it's some NNGP is the acronym. And basically, the idea of the NNGP is that you construct a gram matrix, which is of sample size by sample size, let's say n by n, of your input data. So it's like your images. And then you take this matrix and you construct the gram matrix of the different layers. So for example, this is the gram matrix of the representations after the first fully connected layer. And this is the gram matrix of the representations after the first ReLU. And this is the gram matrix after the second ReLU, and so forth. So the idea is that if you have an infinite width network, you can write down in what seems to be a closed form expression the distribution or the gram matrix of the different representations throughout depth. Okay. Does anyone have any questions about these statements before we proceed? So what's important to remember is that there is a gram of some sort, and the gram is equal to the expectation of some feature vector from a previous layer. Notice the indices here are very important. So here, for example, you have index 2, and here it's index 1, one layer beforehand. And we do the expectation over Z1, which is distributed using with a normal, with a zero mean and covariance K1, where K1 is the previous gram, right? And then we have an expectation of what? Of sigma, which is the nonlinearity of Z1, sigma Z1 transpose. And then there's a scalar here and some matrix here. Okay? Now, after that, we discussed in the previous lecture the neural tangent kernel. So what is the neural tangent kernel? So the idea goes as follows. Imagine you look at the loss of the training, and imagine you look at the derivative of the logits with respect to time. The logits is are the output of the classifier. Now, what we've seen is that you can express the derivative of the logits with respect to time as a multiplication of some gram matrix theta, which is the neural tangent kernel, and some residual, which is the difference between the predictions and the targets. Okay. Now, what we've finished the lecture with was just a very hopefully clear description of what is this matrix theta. So you should think of theta as a kernel that takes as input two examples xi and xj and calculates the following matrix, the derivative of the logits with respect to theta for the xi example and the derivative of the logits with respect to theta for the jth example, which gives us a C by C matrix. So those of you who are doing the homework, in the homework it's very beneficial in the last homework to calculate the dimensions of these different Jacobian matrices. So for example, df to d theta would be a C times P matrix, right? C times P. Okay, so we have these several ideas kind of floating in the air, right? The neural network, Gaussian process, the NTK, and the kernels somehow floating in space. Hopefully by the end of today's lecture, everything will become coherent into a single idea. So here's the main thing about why the neural tangent kernel, or NTK, is an interesting quantity. So in that paper by Jacot and al., what they've shown is that assuming that your nonlinearity is Lifshitz, and we can go into what is Lifshitz nonlinearity, and more importantly, assuming that the number of activations in each layer tends to infinity, then the NTK matrix, which is this theta, tends to infinity, tends to a limit as all of these tend to infinity, which is theta infinity Kronecker product with a I matrix. So in simple words, what does this mean? What does this mean? What does this mean? What does this mean? What are the Ni? Asks Neo. The Ni are the widths of the different layers. What does this statement mean to you? If anything. NTK has a well-defined limit as width go to infinity. Yeah, exactly. That's what it means. Now, notice that this is a non-trivial statement, right? In general, when things tend to limits, you don't necessarily have a limit, right? Especially when you're dealing with these wild nonlinear beasts that we're dealing with. But in this case, one can prove that the NTK tends to a limit, as all the widths go to infinity. At this point, it's unclear what is the significance, but we'll soon discuss that. Now, the next part of the theorem says that what is L? IC is an identity matrix of size C by C. Neo asks, where does the tensor product with IC come from? I mean, it's a bit hard to answer the question without going into the actual calculation, into the proof of the theorem. But it's basically theta is no IC in theta, because there is no IC in theta. I'm not sure what that means. There is no IC in theta. So the NTK is a matrix of size number of examples in the data set times number of examples in the data set. But okay, let me show you again. If you look at the definition of the NTK in the previous slides, notice that the NTK matrix is a matrix of size Cn times Cn. So n is equal to the sample size. So how many examples do you have in the data set? And C is equal to the number of classes. So for example, if you had 50,000 examples in MNIST, the NTK would be 500,000 by 500,000 because the number of classes is 10. So an answer to your question is that IC is the part that's associated with these C classes. Do these words make any sense? Or it doesn't make sense?
So then it means like theta infinity would be an n by n matrix?
Right, right.
Yeah, so does this tell you some kind of mixing kind of property? Because your theta on the left is kind of, it doesn't necessarily have to be this kind of block, right? But then when you do that, it's kind of like mixing of your matrix.
Exactly. Yeah. I like the word that you're using, mixing. Yeah, interesting.
Oh, because there's an analog in
right.
other situations.
Like in what situations? Quantum physics or something?
Yeah, quantum walk on graphs, and you get there's uniform mixing, but it's not has anything to do with this.
Right. Yeah, so I agree with what you're saying. So notice that the second part of the theorem is saying that this theta infinity is equal to the following expression. So it's a sum over all the different layers, and then there's several components to each element in the sum, and hopefully you can identify one of the elements. Which element can you identify? Which element have you seen in your very recent past? Do you see an element you've seen very recently? Very recently.
I guess KL is familiar.
Exactly. KL is familiar. Why is it familiar? Because we've just said that KL is a gram of the features in the NNGP, which is the neural network Gaussian process, right? So this is just a gram matrix associated with the features. Now, what is this whole thing? So let's notice first of all that there is a dot here, right? So the dot means that this is associated with some derivative. If you look at the definition of k dot L plus 1, it's again a gram because it obtains xi and xj. And you can see that it's just defined to be the expectation of dot sigma zi dot sigma zj. And so I think there is a transpose missing here. So basically, k dot is just the outer product of the derivatives of the nonlinear function. Derivatives of the nonlinear function. So roughly speaking, these quantities are related to the backpropagated errors. Because essentially, you can show that the neural tangent kernel has, so if you look at the neural tangent kernel, it's something like the derivative of f with respect to theta times the derivative of f with respect to theta, and there is a transpose somewhere, whereas the transpose, it's here. Now, if you look at a single layer, let's say you pick layer WL, and you look at this df to dWL, it's basically a derivative with respect to a weight. And a derivative with respect to a weight can be factorized into the Kronecker of features and backprop errors. And this is something we've seen a few lectures ago. We've seen why such derivatives can be factorized into features and backprop errors. I guess most of you probably don't remember why this is the case, but at this point it's not very important, so we will not delve deep into this. What's important is to see the high level picture. Can anyone tell me how is this related to the homework. So if you've noticed, there is a homework that is dedicated to Neo and Tristan. We have another dedication. And so does anyone know how is this related to the homework? If anyone has done the homework or read the homework.
You mean homework 9?
I do mean homework 9, yeah. So let us read the description of homework 9. Let me pull it up. Okay, so homework.
One comment is, would it be DFDW and DFDW transpose? Or would it, or am I just confused?
Do you mean regarding the homework, or do you mean
The screen share?
do you mean the bottom equation, like this equation?
Yeah, should there be a transpose on the second DF over D?
Oh yeah, there's a transpose there. Yeah.
Okay, I was just wondering if I'm confused.
Yeah. Yes. Right. So if you look at the homework, the latest homework, it says the goal of this exercise is to investigate the effect of network width on the spectrum of the neural tangent kernel. And essentially what the homework does is it calculates the spectrum of the NTK for increasing widths. So now that you've seen this theorem, what would be a reasonable hypothesis to make about how the measurements should turn out? How should the spectrum of the NTK behave as you increase the width?
Should it converge to the spectrum of this Kronecker product?
Yeah, it should converge, exactly. Now, in the homework, we're not going to check if it converges to theta infinity. We just check the behavior as we increase the width. And what you ideally should see is that the spectrum converges to some limit. So basically, you should see if this is the lambda, and this is the probability of lambda, count of lambda, whatever you prefer to think about, then you should see some type of a spectrum, let's say something like this, and then eventually it becomes very, very close to some limit, right? That means that it converges. Like for small widths, it might look something completely different, but as the width increases, you should see that it converges more and more to a finite, to a certain limit. Does that make sense? It does make sense. Okay.
Can I ask a question?
Yeah.
Is this like independent of the values of the weights, this statement, or this is just at the beginning of training?
It is at the beginning of training. That's a good point. This statement is about the beginning of training.
Okay.
Okay. Now, in homework, you mentioned it converges to, right, so I'll get to that, Amiraz, I'll get to that. I will get to that. Maybe I should make this explanation a bit more proper. Let me just try and do this explanation here a bit more proper. So notice that using chain rule, df to dw can be written as the derivative of f with respect to the output of the network times the H transpose, and then df to dwl. Basically, you can show that it becomes df to dz transpose, Kronecker, H transpose, up to maybe switching the order of the tensor product. And so this thing, let me use a different color. So basically, this thing corresponds to this quantity, and this thing corresponds to this quantity. That's what I was trying to say earlier. It's a bit complicated, maybe, if you're not breathing, auto differentiation of fully connected layers. So I don't want to go into it. But what's important is you see the big picture. The big picture is that there is a limit of the NTK as the width goes to infinity. Now, Tristan touched on a very important point, which is that this statement is for initialization. but we don't actually care about initialization. We care about what happens with training. And so this is where this theorem comes into play. So what this theorem says is, assuming that the activations are Lifshitz and twice differentiable, then as the width tends to infinity, uniformly over t, you get that this NTK tends to this infinite limit. What does this mean? It means that for t between 0 and capital T, so during training, the NTK does not in fact change. Even if you train the network, the NTK is fixed. No, does not. But I recall that there is a, if someone really wants to see a theorem for values, I can show you, I can point you to a source. Oh, by the way, I didn't say what is a Lifshitz function. Lifshitz function means that the sigma, so the nonlinearity applied on x minus the nonlinearity applied on y, I guess in absolute value would be less than some constant times x minus y, right? This means this is the usual definition for Lifshitz. So again, what does this theorem say? This theorem says that even if you train until time t, the NTK still tends to this infinite limit. Does anyone find this bizarre or strange? I feel like Tristan has an expression that shows that he's questioning my statement.
Well, it's so weird that training doesn't affect this thing.
It is very weird, and what we will see is there is a twist. This course has many twists. This is one of them. So this is one of the twists. It is training time, Neo. Yes. So basically, all of these statements are about gradient flow, not about gradient descent. So if you switch from gradient descent to gradient flow, instead of talking about iterations which are discrete, you talk about continuous time. Amireza is asking, is the exact NTK fixed or only the spectrum? The exact NTK is fixed. But the thing is that I wanted to, how people like saying scaffold. People at U of T like using the word scaffold a lot, I noticed. So I wanted to scaffold the homework. Am I using this word correctly? I am. Scaffolding. I went to like a teaching, they teach you how to teach, and they just kept using the word scaffolding. So I was like, I must scaffold. So that's the reason why we were calculating the spectrum, because we're interested in scaffolding. So Luke is asking, what is capital T? Capital T is time, which is basically the time for which you train the network. So imagine if you train the network for, T between 0 to capital T. Does that make sense? Are you looking for like, how does this whole thing depend on capital T? The main message is that the NTK is just fixed. So like for any T, it would just be fixed. That's the message. Does it depend on anything? I don't think so. I don't think so. If you want, I can look at the end of the lecture at the paper, see if I missed something, but it does not depend on anything. This is unbelievable. Near's question is, yes. Is theta infinity defined in terms of kj, which relies on zj? So Stephen is asking, is theta infinity defined in terms of kj? The answer is yes, which relies on the zj minus 1 to be Gaussian distributed. Yes. So doesn't training ruin the fact that zj minus 1 is Gaussian distributed by reading the independence of parameters at initialization? Apparently not. Right. So everything you're saying, Stephen, makes sense, but apparently not. Apparently not. Apparently not. Tristan's shaking his head in disbelief. Again, there is a twist. There is a twist to be seen. Is there a simple intuition for NTKs being fixed throughout training? Yeah, we'll get to that. We'll get to that. Okay, so it seems like at the very, once you question this, it means you understand the statement. So that's good. Now, notice that one of the implications is the following. Imagine if we look again at the differential equation of the logits, right? So here we have the logits and we're looking at the differential equation with respect to time. Do you remember this was the equation from a few slides ago, which said that the derivative of the logits with respect to time is the NTK matrix times the difference between the predictions and the targets, right? So this is just copied from a few slides ago. Now, notice that if this quantity is fixed, then this becomes a simple linear differential equation that we've all learned to love and cherish in courses in undergrad, right? Differential equations. So notice, moreover, that you can actually solve this differential equation in closed form. Like you can just write the optimal solution. And the optimal solution says that the logits, so the closed form solution, assuming that you initialize the network so that the prediction at initialization is equal to 0, the closed form expression can be written as follows. Does anyone recognize what is this? Have you seen this in the past?
Yeah, it kind of looks like the classifier from kernel methods.
Exactly. So what is theta star? Theta star is the solution to the differential equation. So you can think of it as the parameters at optimality. So Tristan is very much correct. This looks like the classifier for kernel methods in machine learning. So let us do a brief jump to introduction to kernel methods. And let us remember this. Okay, this is so, sorry, remove all of this. Look at this equation. This is equation. So here it should be fine. So this equation in the introduction to kernel said something like, you do phi of x transpose phi of x plus lambda I. In our case, there is no lambda I, so let's forget about it. Inverse times y. And then here you have phi of x again and phi of x naught, which is the test point, right? So in our case, phi is associated with the NTK. So phi of x is equal to the derivative of f with respect to theta for this point x and parameters theta. So this thing becomes the NTK matrix, right? And this thing becomes the inner product between the logit derivatives of the train and test data. So take a picture, mental picture of this, and let's jump to the other slides. You see? So here's the same structure. Here, NTK, we just had NTK. Here is the Y that we just saw. And here is the inner products between the test and train data. So do we now understand why is the neural tangent kernel name, why does it contain the word kernel? Because it's a kernel, right? So it's a kernel. What is the kernel? The kernel is phi of x is equal to dfx theta to d theta, right? It's a kernel method. Now, as you might remember, when you were doing your course on differential equations, you have learned that linear differential equations are actually trivial to solve. And the way you solve them is just by doing an eigenvalue decomposition of the matrix that is fixed. It's possible I have a transpose. It's up to a transpose, yeah. Up to a transpose. So as you might have seen in your differential equation course, as the linear differential equation is very simple to solve just by doing an eigendecomposition of the fixed matrix. So you take this matrix, which is fixed, you do an eigendecomposition of this matrix. And after you do the eigendecomposition, you just write the solution as f of x theta at time t is equal to f of x theta star plus, and now you do this exponential of a matrix. Do you remember exponentials of matrices from your linear differential equation courses? You do. And here we just have the residual. So this is just standard stuff in differential equations. Okay? Now, notice that one thing that's cool is that you can plug in, instead of the matrix exponent, just the sum over the exponent of minus t eigenvalue times eigenvector transpose. And that implies that your training is going to converge in certain directions faster than others. For example, if your NTK matrix has one eigenvalue which is very, very large, then you're going to converge in that direction very fast. Okay. Makes sense. Oh, by the way, notice that because we're talking about theta, which is a positive semi-definite matrix, all eigenvalues are positive. And so here you just have e to the minus t, which is a positive number, times a positive lambda, right? So you just, everything converges exponentially fast to 0, but the bigger the lambda, the faster you converge. So what does this mean in practice? It means that you would expect your, SGD training to converge faster on the top eigenspace of the NTK. Okay, so these were the dynamics of the logits. Now, another thing one can do is one can interpret this in the following manner. Imagine if we just presented the NTK as follows. Take your neural network classifier, which is f of x theta, and imagine we just linearize the model. F of x theta converges in exponential time. Yes, that is what it says. Yes. Yes. So again, what is the bottom line of the NTK? The bottom line is, imagine you take your usual network, f of x theta, and imagine that you linearize the model. How does one linearize a nonlinear function? Just by doing Taylor, right? Just taking the first Taylor order. So you do f of x theta, bar stands for the linearization, is equal to f of x theta 0. So this is initialization, plus j, which is a Jacobian, df to d theta times theta minus theta 0. Do you recognize Taylor series that you've learned in some course at some point in time? Now, the fixed Jacobian is df to d theta at theta is equal to theta 0. So it's basically the derivative at initialization. And what the NTK is telling us is that essentially this matrix is fixed. Now, notice that we can take this Jacobian and this f bar, and we can just write the loss. So the loss of f bar and your target y is just the mean squared error loss written here. I always forget the half, right? So it's half of f bar minus y. And imagine that we just look at the dynamics of the oh, Gina has a question.
Oh, never mind, I answered it. For a second, I thought you forgot to multiply theta, because I thought you were doing j of theta, but never mind, that's multiplying.
Yeah, so that is exactly, it is multiplying. Yeah. And so imagine if we now look at the dynamics of the parameters with time, we would get d theta to dt is minus Jacobian transpose f bar x theta minus y. Why? Because basically it's just, it's just simple derivation, right? Simple derivation. because if you derive this quantity with respect to theta, then you need to derive this quantity with respect to theta, and the derivative of this quantity with respect to theta is just literally j, right? So you just do j transpose times f bar x theta minus y. Is this clear? Clear? Yeah. Okay. And so notice that at this point, we can look at the dynamics of the logits. And if you write the dynamics of the logits f bar with respect to time, using chain rule, you get df to d theta times d theta with dt, right? Just chain rule. And then if you plug instead of d theta to dt, the previous equation, so this is d theta to dt. I guess I should highlight this. So this is d theta to dt. I plug it here. I get this, this quantity, right? And then also I have df bar to d theta. So that's just this quantity, right? And so what did we get in the end? We get JJ transpose is just the NTK by definition, because you can see here, right? The JJ transpose is the NTK. So at the end of the day, you get NTK times F bar minus Y, right? So this is the equation that we've already seen. But why is this point of view very illuminating? Can anyone see? Why is this illuminating, interesting? Or is this not interesting? That's also a possibility. To me, this is the simplest way to think about NTK.
Hi, Professor. I'm quite confused about the dynamics of parameters. So you have theta, the theta over delta t, but well, I thought it should be delta L over delta t, but like where does this delta theta come from?
It is DL. So d theta to dt is equal to minus the gradient of the loss with respect to theta. And so you need to derive the loss with respect to theta. So this is the loss. And you need to derive it with respect to theta, right?
Okay.
And so if you derive L2 squared, you just get, you know.
Yeah. But how can we write minus delta gradient L like d theta over dt? Where the notation for me?
Which notation don't you like?
Like d theta over dt.
Which notation would you prefer? I can custom the slides for your taste.
Just the right hand side.
Oh, you like the right hand side better. But we are talking about continuous gradient flows, so it makes sense to talk about the derivative of the parameters with respect to time. No? Like in gradient descent, you write theta t plus 1 is equal to theta t minus step size times the gradient with respect to theta.
Yeah.
And in continuous time, you just write d to dt is equal to minus gradient of the loss theta.
Oh, I see.
Okay.
Oh, thanks.
So does anyone see why is any of this interesting? Like, why is this perspective of linearization useful? If it is useful, maybe it's not useful. Generalizes to infinite width. Not sure what you mean, Jack. What does it mean, generalizes to infinite width? Since the NTK matrix is fixed, as width tends to infinity,
Is it because it's similar to what we had on the previous slide without linearizing?
Yes. So Amirez is saying NTK contains only first order information, and since NTK is fixed, the result is invariant if we approximate F linearly. I think this answer of Amireza contains all the correct words. Basically, what this slide is telling you is that if you were to linearize your network, then the dynamics would be equivalent to the dynamics of NTK, right? because this is just NTK dynamics, right? NTK dynamics. So essentially the NTK is equivalent to just linearizing a nonlinear model. Does that make sense? The model is being linearized. So you see here, F bar is the linearized model. So it's replacing f of x theta with f bar of x theta, which is just fx theta 0, where theta 0 is initialization, plus Jacobian times theta minus theta 0. There is different perspectives on the NTK. You know, one of the perspectives is what's written here, which is that you have this linear differential equation on the logits, which can be solved in closed form expression and so on. That's like one point of view. A different point of view is that the NTK can be interpreted as a linearization of the nonlinear network. It's like if you linearize the nonlinear network, then you obtain the NTK dynamics. Does this mean you can treat a deep net as a perceptron in some sense? I'll get to the meaning very soon. So notice that the NTK is in fact highly related to the Fisher information matrix, because the NTK is equal to the derivative of f with respect to theta times derivative of f with respect to theta transpose, right? So this we've seen many times. And in previous lectures, we've seen that the Fisher information matrix is equal to this quantity, right? This is just from a previous lecture. Now, assuming that we're using MSC loss, then under MSC loss, the loss is equal to f minus y L2 squared divided by 2. And so the second derivative of the loss with respect to f is just equal to an identity. So this whole thing is just meaningless, right? The second derivative of the loss with respect to the logits is an identity. And what you get is a df to d theta transpose times df to d theta. So notice that this quantity is the same quantity as this, except the order is switched, right? Order is switched. So some people like calling these companion matrices. Have you heard this name, companion matrices? You have. So what does it imply that these matrices are, you know, one is like A transpose, the other one is A transpose A. It implies that same non-zero eigenvalues, right? Because the eigenvalues of A transpose are equal to the eigenvalues of A transpose A if you look at all the non-zero eigenvalues. One of the matrices has a larger null space, but if you look at the non-zero eigenvalues, that's the same spectrum. Now, why is this interesting? What is the significance of this? The significance is that the Fisher information matrix is related to the Hessian, right? It's basically a part of the Hessian. And the Hessian represents to us the landscape of the loss, right? The Hessian is basically this thing. It's like a quadratic, it's a representation of the quadratic ball in which you're at. And so if the Fisher information matrix is fixed, or if the NTK is fixed, it implies that the Fisher information matrix is fixed, which implies that the Hessian is fixed, and therefore the whole landscape is just a quadratic ball. So deep learning training is equivalent to optimizing this thing. Amreza is asking, can we say in general for infinite width networks, there is no difference between the network itself and its linearized version? We will see, Amreza, we will see. As I present it currently, it seems like what you're saying is correct. But we will see, there is a twist. What do we know about the spectrum of the NTK? I don't think anyone actually measured it. So you guys are going to measure it in the homework. In the homework, you will be able to answer your question, you. But a reasonable guess would be that the spectrum of the NTK is equal to the spectrum of the Fisher information. And in previous lectures, we've discussed the spectrum of the Fisher information and so that it has a bulk and outlier structure, right? And there's a set of outliers. The number of outliers is equal to the number of classes and so on. So that's kind of what you expect to see, even before doing the homework. Yeah, so all of these matrices are positive semi-definite by definition, because whenever you have something like AA transpose, it's always positive semi-definite. Okay, so we're about to run out of time. So I want to mention that there were certain people, Sanjeev Arora and co-authors, who actually found a way to calculate theta infinity, like literally theta infinity, not by approximating theta infinity by taking the width of the network to infinity, but just analytically you can calculate it. And what they did was compare a network that is, in this NTK regime with a regularly trained network. And here's what they report. So let's focus on these two columns first. So CNNV, CNN is just a regular convolutional neural network. CNTK is the convolutional neural tangent kernel. So basically, this is what we're talking about just now. And this is the usual network, usual NTK. And they were interested how much of a difference in performance is there once you increase the number of layers. And what they've observed is that the CNN, initially the NTK gets better performance in depth 3. But as you increase the depth, the usual training of a neural network outperforms an NTK network. NTK network is basically a network that's, you can think of it as a network that's linearized, or you can think of it as a network that literally solved this quadratic approximation of the loss. There's different ways to think about it. So do you observe something strange in this measurement? Is something here confusing maybe? I mean, everything you guys are saying is correct, but the first observation is that the accuracy is not equivalent, right? Like under what I've been telling you this whole lecture is that NTK should be equivalent to, like, neural networks are supposedly in this NTK regime. So supposedly the performance of a neural network should be equivalent if you just linearize it, or if you just optimize in a quadratic ball, right? But you can see that the performance is in fact not equivalent. Right? So you would expect these two columns to be the same if NTK was, truly what's happening in deep learning. You can see here two columns. Gap here stands for global average pooling. So it's basically a very similar experiment that again shows that the two methods don't perform the same. So to summarize, if you have an infinitely wide network, then you can think of a network as being a linear model because you can essentially linearize it. And this can be thought of also as a kernel method where the kernel is defined through this df to d theta. And essentially, all of this is pointing to the fact that deep networks are linear models, right? It's just linear models with a certain fancy kernel. And the question is, you know, is this truly what's happening in deep learning? Are deep networks truly just a linear model? Or is there something that was omitted purposefully throughout this lecture, which would explain the gap between deep networks and neural tangent general? Suspense, yes. Okay, so this is the end of the lecture. Thank you for joining, and I shall remain for questions. Can the TA post the marks? Yes, 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 yes. But it's pretty like clear if you did the homework correctly. Either see a phenomenon or don't. No. Is it clear?
Can I ask a question
Yeah.
about gradient descent?
Yeah. It seems like you're stuck or I'm stuck.
Sorry, my internet froze.
Oh, okay, yeah.
Oh, I was wondering, I was thinking about this morning about mini batching. So when you do mini batching, you randomly divide them into pieces, and then you calculate the small loss, and then you kind of do it that way. Would it be equivalent to stochastic gradient descent, or would it be a little bit different?
Stochastic gradient descent is mini batch gradient descent with batch size equal to 1.
I see. That's interesting. Yeah, I was just hoping that I could get away with just doing batching because the system doesn't perform very well with big batch. Maybe I have to look a little bit. Is there work that, for example, says that it's a good approximation of the gradient flow in some sense? That when you do empirical experiments, you can use batching.
So there's several things. There's gradient descent, which is usually denoted GD. There is mini batch GD, and there is stochastic GD, right? So here the batch size is equal to the whole data set. Here the batch is equal to a part of the data set. So let's say 128 images. And here the batch size is equal to 1. Now, gradient flow, so all of these are discrete. They have discrete steps. Gradient flow would have, I mean, by definition, gradient flow would have a batch which is equal to the whole data set.
Right.
And then there's people who are trying to, to create like a stochastic differential equation, which would be equivalent to mini batch GD. And there's various ways in which people do that. Various ways. Is that what you're referring to? So this is continuous. Does this make sense? No.
Yeah, that makes sense. I guess I just have to, yeah, I just find it a bit annoying that when I try to train the model that I was building, I calculated, so I converted it to the binary classification thing. I figured out how to do the logistic. You have to hit it with like a log plus, and then you have to do soft plus and something else, but it's not that hard. But then I realized that it's really hard to train the network to 0 to like 100% accuracy when you do gradient descent on a batch, like on a batch of everything.